Welcome to Section 2, Introduction to Fraud Detection. This is Lecture 6, where we look at managing labels within a fraud detection context. So in the notebook, I've replicated the steps from the previous lesson where I've just read in the CSV as a data frame. And within fraud, what we are frequently interested in finding out is how many fraudulent records do exist from a historical perspective, right? So we know that the number of fraudulent records can be identified by looking at this class column, which is the label from a machine learning perspective. And in pandas, we can actually just select that column and then apply this value counts method on it, which works nicely in the sense that it gives us an output where the unique values within that column have a kind of a group by with a count applied to them. So we know all of the records with a 0 within the class column, there are 284,000 of them, and those with a 1, which are the confirmed fraudulent records, there are 492. So previously, when I mentioned a severe class imbalance, we can see here that 284,000 versus 492 is quite significant, especially when it comes to a machine learning problem. Now I'll explain to you why that is. So if we are training a model, what we're going to find is that our algorithm that we use would very likely become overwhelmed and biased towards the majority class, which is the normal class. So it might end up learning patterns of the majority class only, while neglecting to pick up much on the minority class. And that would be a problem, and we'd see that when we actually evaluate the performance of the model. Right? So we wouldn't be able to learn anything meaningful from the minority class, but we can cater for this imbalance. There are a number of ways to do this. One of them is to upsample the minority class at training time. So, we've got our set of training data. There might be a few hundred instances of fraud, but can we use techniques to generate synthetic copies of that? There are a number of approaches. One of the popular approaches is SMOTE, which is synthetic oversampling of the minority class, right? So that's one approach. Another is to downsample the majority class. So that's to say, well, if I've got 284,000 good records, can't I just cut that number in half, make it 100,000 or make it 10,000? Let's train a model and see if that solves the issue, right? So that's the second approach. A third approach might be to use a different modeling technique. So there are approaches called anomaly detection algorithms specifically to solve these kinds of problems. Normally how these are prepared are they are trained in an unsupervised fashion, meaning they're trained without labels. You save all of your labels for the testing phase of the modeling process, and then you can evaluate the effectiveness after you've trained the model in an unsupervised fashion. So that's one of the ways that you can solve it. Lastly, what you can do is rebalance the classes at training time using the algorithm's class weight hyperparameter, if it does have one, to penalize the loss function more for misclassifications made on the minority class. All right. So what that means is when the model is learning from its mistakes, so if there's misclassifications, you're going to penalize those instances for the minority class a lot more than you're going to penalize it for the majority class. Basically telling your algorithm to pay more attention to the minority class, don't get it wrong, learn more about it. And that has proven to work quite well in a supervised learning context as well.